Okay. If you Professor Ikeda, are you ready?
Yeah, I'm ready.
Uh, okay. Okay. Let us start today's seminar. Today, Professor Kâzim İlhan İkeda will give a talk about on the Lagrange reciprocity and functoriality principles. Please welcome.
Thank you very much. So, and thank you for inviting me to give a talk in Knots and Representation Theory seminar series. So today I will tell about Langlands reciprocity and functoriality principles, mostly about my own reflection on this subject. I mean, as you all know, I mean, the basic approach to reciprocity and functoriality principles is via trace formula and Shimura varieties. So I will tell something, not unrelated, related of course, but another point of view. So let's start our talk. So this is the outline. In the first part of my talk, I will going to make a construction about topological groups, basically. And in the second part, I will tell about automorphic Langlands group of a number field. Automorphic Langlands group is a hypothetical group, by the way. I mean, it is expected, but I mean, we don't have the exact description yet, though James Arthur has a nice candidate for automorphic Langlands group LK, by the way. And in the final part, I will talk about reciprocity and functoriality principles based on the first two parts, basically. Okay, so let's start our discussion. So I'm sure you all know free product of topological groups because most of you, I believe, are working in geometry, topology, algebraic topology, and so on. And free products appear in these subjects that I'm quite sure. So first, let me fix the notation. So I have a collection of k omega topological groups. This k omega condition is put for some technical reason. So I have to recall the definition and its basic properties, although I will not tell very much, but emphasize and why we need them. And in this indexing set, I will fix for each I, not in a finite, distinguished finite subset, open subgroups, OI denoted by OI, and I sub infinity is, I'm sorry, is the finite subset of the indexing set for which these open subgroups are not defined. I mean, there is, I'm sorry, there is a reason why I am making these assumptions. Further, I will put some more extra assumptions also. So I am sure you all know the free product of the collection GI. They come together with canonical embeddings of each GI into this free product. And from the work of Graev, and Morris, we know that free product of the collection exists in the category of topological groups. By the way, I mean, this category is not a very nice category, by the way. And it seems that this is one of the reasons that Clausen and Scholze, they are developing this condensed mathematics subject to deal with this kind of categories. So free products, what they have is they have a universal mapping property. So if H is any topological group, together with continuous homomorphisms from Gi to H for each I, then we have a unique continuous homomorphism from the free product to H, such that when I compose with this embedding, I recover the phi I homomorphisms. Right. Now I will go further and define restricted free product of topological groups. So the starting point is, as a first step, in our indexing set, we choose a finite subset S, but with the condition that this distinguished finite index set I infinity that I introduced in the notations here, the finite subset consisting of all I for which this open subgroup is not defined, this I infinity should live in this finite subset S. For every such choice, we have the topological group GS, which is the free product of OIs, so I not in S, and free product of GI, I in S, and we take the total free product. And we denote this topological group by G sub S. So suppose that I have two finite subsets S and T, satisfying the property that I infinity lives both in S and T. And if we have these chain of inclusions, then we have a continuous homomorphism by the universal mapping property of free products. So the reason is that the canonical embeddings, together with this one, if I is not in S, combined with mapping, universal mapping property of free products of topological groups, implies the unique connecting map from GS to GT. So we define the restricted free product of topological groups, which we denote by this symbol as restricted direct product kind of notation, but instead of product, we put star. This is defined as the colimit of this system of GS and connecting maps, tau TS from GS to GT. Now, the topology, we want to put topology on this colimit, and it is defined by declaring that X is open if X intersected with GS for every S is open. This is how we define open set. So endowed with this topology, this restricted free product becomes a topological group. So there is one technical issue here. At this point, we have to assume that I is countable, and moreover, this GI topological groups, in the beginning, in the notation, we assume that we choose them as K omega group. This is the reason why we choose K omega topological group, because otherwise, if we don't assume every GI to be K omega group, then this colimit will not end up to be a topological group. It will be a group which is quite close to topological group, but it will not be. But whenever each of these GIs they are K omega, then this becomes a topological group. Yeah. In fact, for the reference for this, one has to look. Wait a second. Let me show the reference is. Oops. The reference is this one. Final group topologies, Kac-Moody groups, and Pontryagin duality of Glöckner, Gramlich, and Hartnig. This is the paper. And regarding K omega spaces, probably the main reference and the only reference is this paper. So what's a K omega space? So it is union of countable union of compact subspaces are X. If X is a K omega space, then X is countable union of compact subspaces, and each Ki, let's denote them by Ki, should live in K n plus 1. And if U in X is any subset, then when we intersect, then it will be closed. So it has such a definition. So let's return back. So these are the reasons that we put these assumptions, so that this restricted free product, when we put the direct limit topology, becomes a topological group. So this is kind of important. So now restricted free product of topological groups, they have also they satisfy universal mapping property, as in the case of free products. So if H is a topological group, and if we have collection of continuous homomorphisms from GI to H, then, we have a unique continuous homomorphism phi S from GS to H, and we have a continuous homomorphism by passing to the direct limit to H. And this phi, this continuous homomorphism, satisfies this property that when we compose phi with the canonical homomorphism CS, which comes along with the direct limit, we recover phi S. This is the first part of the universal mapping property, but it goes on more. Second fact is, so to simplify the notation, let this script G denotes this restricted free product, and script GI denotes GI. So for each I, there exists a natural continuous homomorphism from GI to script GI to script G, which is defined via this commutative triangle. The interesting thing is that this S, which is a finite subset, does not depend on the choice of our S. I mean, in the first run, this fact seems to depend on S, but it turns out that it is independent of the choice of finite subset S of I containing I infinity. I mean, this is quite important, because if H is a topological group and we have a continuous homomorphism from script GI to H, then it turns out that we have a triangle like this. Here, phi is the unique continuous homomorphism given by the universal mapping property. Therefore, we have quite a similar universal mapping property like in free products. So if we have a family of continuous homomorphisms from GI, so which we denote by script GI also, to H, then we have a unique continuous homomorphism from script G to H. Now, one of the basic facts is that if phi prime from script G to H is a continuous homomorphism, so that when I composed with this Qi naught, which was defined to be this canonical, which first depended on S, but it's independent of such choice. When I compose with Qi, with phi prime, if it is equal to phi I, then phi prime and phi, they are the same. This is kind of, we will use it later also. So we have two topological groups, G and H, and continuous homomorphism from G to H. We define H conjugates to Xi. So Xi prime. So if I compose with the inner automorphism of H, like this. So obviously their kernels coincide. So if I have my script G, a continuous homomorphism from script G to H, a continuous homomorphism phi prime from script G to H is called locally H conjugate. If phi prime and phi, when I compose with this canonical mappings from script GI to script G, to phi prime and to phi, if the resulting maps from script GI to H, the one will be phi prime I and the other will be phi I. If they are H conjugate, then we say that phi and phi prime, they are locally H conjugate. Locally. Now, there is one important fact. If phi and phi prime from script G to H, they are locally H conjugate, then their kernels coincide. Well, this is, how shall I say? Well, I mean, there are certain technicalities here, but I mean, one can prove this. One of the reasons is that the topology in script G is defined as we say that a subset is open if its intersection with G sub S, they are all open for every S. So in particular, so if I choose, how shall I say, the direct limit, then it will be a closed, the arrows will be closed because GS, they will be open, right? But open subgroup is also closed in a topological group. One has to use that fact here. Now, why we did all this universal algebra thing? Because when we abelianize the restricted free product, we get the restricted direct product of the abelianization of GIs and abelianization of OIs. So restricted direct product of certain groups, they, how shall I put it? appear in centrally in algebraic number theory, actually. So how? How does it appear? So we choose our indexing set I as the set of places of a global field K. So what's a global field? In this talk, I will restrict my attention to number fields because function field case is simpler. That's the point, I mean. So number field case is the problematic part. So I will concentrate on a number field. So what's a number field? Finite extension of Q, the rational numbers, and places correspond to primes in the ring of integers of K, non-zero primes in the ring of integers of K, or infinite primes. So what they are the embeddings of K into the field of complex numbers. Some of them are real and some of them are complex among these embeddings. So primes together with these embeddings, the real ones are one of them, and we have two R2 of them where we couple complex embeddings via complex conjugation. They are the set of places of the global field of the number field K. So our index set is primes here. And I infinity here as finite set consisting of all infinite places of K. So these are the embeddings that I described. And together with some finite number of prime ideals. And for each I, OI is, we have for each I in the complement of I infinity, we have certain topological groups so that they are, how shall I put, when I complete it at I, so there is something called completion of a place. So what is that? If it's a prime, so it's defines, so if our prime is P, it defines p-adic absolute value, we complete it accordingly. If it's an embedding, we have the usual absolute value, real absolute value or complex absolute value. Then we first embed it and then complete it. We have certain topological groups so that the abelianization is isomorphic to this multiplicative group of the completion of the global field K for all places I, and whenever our place is not infinite, so it's a finite place, then the abelianization of the open subgroup is isomorphic to the unit group of the completion of K at I. So I is a place here. So Ki is a p-adic field. So we have the unit group. So if you have QP, the p-adic numbers, you have ZP, and inside ZP, the multiplicative group, the ones whose p-adic norm is 1. So it is clear that when we plug in this setting in the abelianization, we end up getting the ideal group of K. Ideal group of K is an extremely important group appearing in algebraic number theory. So this is nice, right? So we say that, okay, it's a non-commutative generalization of the ideal group and so on. But in order to do such a non-commutative generalization of the ideal group JK of K, this is only possible if we have a reasonable local non-abelian class field theory over K nu, but not in the sense of Langlands, but in the sense of Hasse, so in the classical sense, for finite places of K. So, yeah, I mean, Langlands correspondence or Langlands reciprocity is local non-abelian class field theory over K, but there is another local non-abelian class field theory of the local field K nu, which is done by, actually, let me wait, pass, where, oops, which is done by Fesenko, non-commutative local reciprocity maps, and Koch, Deschalit, they do the meta-abelian case, meta-abelian local class field theory. And in full generality, by these two papers and Lobby. Yeah. So, as you see, how shall I say? Uh, if we have Hasse type non-abelian, local non-abelian class field theory, so what this means is that we have a reciprocity law between Galois group on the one side and on the other side a group which is constructed just via the data on the ground field K. So class field theory is fantastic because of that, actually. I mean, all the arithmetical information in the abelian extensions are coded in the ground field K. So because of, I mean, it's like Cauchy integral formula kind of thing, right? And if you know the boundary, you know the interior point value. Yeah, I mean, so now, as I said, K is a global field. Now I will specialize to a number field that I said K is a finite extension of the rational numbers. And we denote the set of finite or Henselian, they are the same, place of K by HK or FK. And the set of all Archimedean, that's infinite place of K, we denote by AK or infinity K. And K sub nu denotes the completion of K at the place nu. So in case we are in the Archimedean setting, K nu is either real number field if the embedding of K into complex numbers is inside reals. Else, if the embedding is not inside real numbers, then the completion is C, the complex numbers. And if our place nu is a Henselian place, then completion is a finite extension of the field of p-adic numbers QP, where P is the intersection of Z and the prime ideal that we are considering. So algebraic function field case is, I mean, we can develop in the same shelf. Because of that, I put infinity K and Fk because there is no Archimedean place in the function field case. Because every place is Henselian. No Archimedean components, the theory that we will develop. So in that sense, it is, I mean, one can work out together the theory. So, okay, so how local non-abelian reciprocity map of K nu? K nu here is completion of nu at a finite place, so Henselian place. So there are several ingredients that we have to do. First, we have a Henselian place, nu, and we complete K with respect to nu, so we have local field K nu. Then, if you consider the maximal separable extension or algebraic closure, this time it's characteristic zero, uh, inside it we have the maximal unramified extension, which is abelian in the local case, and it is procyclic, generated by Frobenius actually, phi that we denote by phi k nu. So it is an automorphism from maximal unramified extension k nu nr to k nu nr, and we extend it to k nu sep. We extend it and fix such an extension. It is called Lubin-Tate splitting, by the way, for some reasons that I will not tell. Now, the central to this theory, local non-abelian reciprocity map, there is a topological group, nabla. It depends on this choice of Frobenius automorphism, the lifting of this Frobenius automorphism. I mean, the Lubin-Tate splitting. Well, by the way, I mean, even if we change the Lubin-Tate splitting, I mean, there is a relation between this nabla, phi k nu, and the other lifting, nabla k nu, the other lifting. So, I mean, this is okay, a restrictive kind of assumption, but in the end of the day, I mean, they end up all to be isomorphic, so it's not a big deal. Now, the construction uses the theory of APF extensions of fields of norms functor of Fontaine and Wittenberger. And this is the precursor of Scholz's perfectoid space theory, by the way. So, well, I will not explain what this nabla is exactly, but let me very briefly give you an idea. So, you see, if you consider G K nu, the absolute Galois group of local field K nu, it is pro-solvable. So we can build up or the uh, absolute Galois group by considering successively abelian extensions. So we consider first the abelian extension, and then we consider the other extension whose solvability degree is 2, so it means two-step abelian extension, and it go on like this. And this will recover G K nu, the absolute Galois group of K nu. And this were Koch and Deschalette here. Where is it? Yeah. Meta-abelian local class field theory. They develop local class field theory for the maximal meta-abelian closure of K nu. And actually, this paper contains the fundamental idea how to go further. And one breakthrough also made is by Fesenko in non-commutative local reciprocity maps. Wait, where am I? Yeah, here. I'm here. Yeah, I mean, I'm here in the page. So the idea is, instead of considering, that's the idea of Koch and Deschalette. But later on, Fesenko observed that instead of considering just successively abelian extensions, it is possible to consider certain types of extensions of K nu. They are called APF extensions. So what's an APF extension? APF extension is something like this. So when we consider an extension of K nu, we have two types of ramification filtrations. One is lower ramification filtration, and the other one is upper ramification filtration. Now, both of them have their own strength. I mean, first we define the lower ramification filtration and realize that lower ramification filtration is quite nice when we take intersection. But via Herbrand function, when we define the upper ramification filtration behaves well with respect to taking quotients. Therefore, passing to the projective limit, we can define not only ramification filtration of upper ramification filtration of finite extensions, but also to infinite extensions, and in particular, upper ramification filtration of the absolute Galois group. So in that sense, I mean, upper ramification filtration is very nice for infinite extensions, infinite Galois extensions of the local field, K-nu. However, there are certain types of APF extensions that we can define lower ramification filtration for those infinite extensions also. They behave well with respect to taking quotients. They are called APF extensions. And what Fesenko observed is that APF extensions, as in the case of meta-abelian extensions and tri-abelian extensions and so on, they recover the maximal uh, uh, algebraic extension. And not only that, the theory of Fontaine and Vintemberger developed yields certain groups actually in K-nu, which together with these APF extensions, they give some reciprocity map kind of thing between nabla, not K-nu, but this is the one which is the limit of these nablas for each APF. One can take projective limit. So this is the one which is isomorphic to the maximal, absolute Galois group of K-nu. We have such an isomorphism. Well, I mean, this is not just an isomorphism. I mean, there are many ways to, one can write group theoretically describe this absolute Galois group, local absolute Galois group. I mean, there are works of Wimberg and so on, Demuskin and many prominent mathematicians. They described group theoretically local uh, absolute Galois group. But this isomorphism has some features like this. This nabla depends only on the ground field K-nu, the definition of nabla. And moreover, it has properties quite similar to local abelian norm residue map. So norm residue map I say as the inverse of the Artin, local Artin map. And also we have the Weil form of this. This is class field theory people or Langlands people. They prefer to use Weil group, local Weil group instead of absolute Galois group, because here we have to pass to profinite completion. But in the Weil form, which exists also, this is a subgroup of this, but the topology here is a bit different than the topology in here. Is topologically isomorphic to the Weil group. And again, they have similar class field theoretic properties. So, for example, one of the important property, and that we will going to use is we have the upper ramification filtration for this group nabla. For the for the Galois form, we have also upper ramification filtration. But since I am interested in Langlands reciprocity and functoriality, I mean, I prefer to use the Weil form. So we have a certain subgroup. So there is a chat. What is the reference 9 on slide 20? Let me check. This one. Reference 9. Wait. 1, 2, 3, 4, 5, 6, 7, 8, 9. This one, ramification theory. This, I hope this is okay. I don't know why it gave numbers, but it doesn't give numbers to, wait. Yeah. So we have the upper ramification filtration, and the one that's important to us is the one corresponding to inertia, where all ramification data lives inside in the inertia group. So to summarize, there is the following table. So let me show you this table. So first, abelian local class filter, the well-known theory. So we have the abelianization of the absolute Galois group of the local field K nu. Then it is via Artin reciprocity, it's isomorphic to the profinite completion of the multiplicative group of K nu. So if we consider the Weyl group, abelianization of the Weyl group, local Weyl group, then we don't have profinite completion. It's isomorphic to K nu star. So we have upper ramification, zeroth upper ramification filtration. So under the reciprocity isomorphism, under the Artin map, it's isomorphic to the unit group. So more generally, I mean, if you choose any delta real number in between I minus 1 and I, this is half open, half closed interval, then the upper ramification filtration delta is ui here. Now, in the non-abelian setting, where, first of all, I should say that, so if you take the abelianization, all of these cells match here. So abelianization of GK nu is this. So, and these ones also. And not only that, abelianization of the non-abelian local reciprocity map that is stated here. This is norm residue arrow, by the way, or that is stated here. When you abelianize, you end up in the Artin symbol. So here we have this isomorphism. GK nu is isomorphic to this nabla. Weyl group corresponds to the subgroup nabla Z. Upper ramification at 0 is nabla 1. There is no this part. Unramified part dies. We have this. And higher ramification filtration in upper numbering. Here, but one has to be careful here. I put here, this is constant 0, but here I underline is a certain sequence, and this is the projective limit of that upper numbering nabla once. So, I mean, anyway, details exist in that paper. So, having summarized, yeah, this is Hasse type local non-abelian reciprocity map, by the way, not Langlands type, although they are quite close related actually. So, let's get back to our Langlands story. So, first of all, we have the zoo of, how shall I say, Galois groups. We have Galois group and Galois group's cousins. I mean, one of the cousins we have met, it is the Weyl group. And another cousin is the Langlands group, or Weil-Deligne group, let me say, and Langlands group. Well, there are other cousins, and all of them are related, like motific Galois group, and nowadays physicists are very much interested in something called cosmic Galois group, and there is Grothendieck-Teichmüller group, and so on. There are those arrows between them, and every one of them are somehow connected. And on the far left, the one that's living is the Langlands group, and let's say distant cousin, maybe, whose existence in the local case we know it is defined by the local Weil group, and we take direct product with SU2R or SL2C. I mean, this is the compact real form, so I prefer, since this is compact, I will use this one. And if it is Archimedean, our place, this is the Henselian finite place. If it is Archimedean infinite place, then we just take the absolute Langlands group to be the Weil group. So what is that? It is when our infinite prime is complex. So K nu then becomes C. The Weil group of C is just the multiplicative group. And when nu is infinite real place, then completion is real number field, and Weil group of R is the certain subgroup of Hamilton quaternions, C cross the multiplicative group, and J is the element in the Hamiltonian quaternion times C star. It is this one. So one remark maybe is that how we ended up defining Weil group of K nu in the Archimedean case is that we just mimic the same short exact sequence that Weil group satisfies in the local field, finite extension of QPI, or let me say Henselian local field case. We have one to inertia, and then Weil group F, and then Z, that's the cyclic group generated by Frobenius, and to 1. We have this short exact sequence. So we mimic that, and then immediately we see that when we mimic complex number field has absolute Weil group C star, and real number field has absolute Weil group, this one. Yeah. So we fix a Lubin-Tate splitting phi for finite prime. Then local non-abelian norm residue isomorphism, as I stated here, this one. Oh no, not this one. I'm sorry. This one. Yeah. Hoppa. Yeah, here. Induces an isomorphism. So I take direct product of this with a copy of SU2R. Then since we have this isomorphism, and since for the finite prime nu, the local Langlands group is defined to be the Weil group times SU2R, we have an isomorphism between LK nu, the local Langlands group, and this topological group. And nice thing is that this is kind of, again, a non-abelian norm residue isomorphism, but this time not in Weil form or Galois form, this is in Langlands form, because on the left side, this group is constructed just from the data from K nu, while LK nu is kind of uh, a Galois group kind of thing. So this is like a class field theory isomorphism, but non-abelian, of course. So we call this the Langlands form. So because of that, I put here Langlands. So what is Weil-Arthur ideal group of K? Now, this answers the question that we posed here. Let me put it here, show it again. Y restricted free products. Such a non-commutative generalization of the ideal group JK is only possible if we have a reasonable local non-abelian class field theory over K nu in the sense of Hasse for finite places nu of K. So keeping that in mind, now we define Weil-Arthur ideal group of K. This is an unconditional non-commutative topological group. It depends on a family of Lubin-Tate splittings and defined by the restricted free product of this group. So what is this group? This group is, as you see, isomorphic to LK nu and with respect to this group is like the in the abelian case. So when I abelianize, I want this part to be equal to or isomorphic to UK nu. Therefore, I take the ramification subgroup at 0 in upper numbering of nabla, of the Weil, nabla Z, let me say. This is isomorphic to Weil group, but this is not Weil group, by the way. And this is isomorphic to the inertia, but of course this is not times SU2R. And this is for the finite part, and for the infinite part, we directly choose WR. This is a certain subgroup of the Hamilton quaternions. But how many copies we free producted? R1 copies. R1 copies is the number of real embeddings of K into C. And R2 copies of the Weil group of the complex number field, and 2R2 is the number of complex embeddings of K into C. So from the discussion that we did before, this can be considered as a non-commutative generalization of the ideal group GK of K. Why? Because when we abelianize it, we get GK. Yeah. So this is indeed a unconditional. There is no, how shall I say, conjecture or anything. I mean, this is unconditional, non-commutative topological group. But I have to say that the topological group is not an extremely well-behaved topological group in the sense that, how shall I put it? I mean, it is not, it is quite, the topology should be quite messy, I believe, yeah. So having defined Weil-Arthur ideal group of K, now we have the global counterpart of the local Langlands group. It's called automorphic Langlands group. So why it is quite central in the Langlands program? Because representations, let me say, finite dimensional semi-simple representations, complex n-dimensional representations of the group LK, their equivalence class of such representations should be in bijective correspondence with the automorphic representations of GLN, the adelic GLN, uh, up to equivalence, but not all automorphic representations, unfortunately. We have to consider restrict to a certain subclass like temperate. So temperateness is a certain condition on the image of this representation of automorphic representation. Uh, for you see, I mean, if one wants to insist on to consider all of the automorphic representations, then one has to consider Arthur parameters and such things. Here we are in the Langlands parameter level. Okay, so, but at any rate, I mean, even in the case of Arthur's, how shall I say, uh, level, one has to use LK, the Langlands group. Therefore, I mean, this is kind of quite central. So let us assume for the time being that this hypothetical automorphic Langlands group, suppose that it exists as, yeah. So as the Langlands group LK should behave very much like Weil group or Galois group, there are some formal properties that LK is expected to satisfy. And I mean, one of them is if I choose an embedding of K-sep in K-nu sep, K-nu sep is larger than K-sep, of course, it's dense. Uh, this determines a homomorphism from LK-nu to LK by restriction. It's and up to LK conjugacy, of course. Uh, so we call this homomorphism E nu Langlands. Therefore, for each Henselian place nu, we have a homomorphism from this group that we introduced. Where is it? Here. Or here, yeah. In the non-abelian norm residue in Langlands form, we have an isomorphism to LK nu, and let's compose it with E nu Langlands to LK. Therefore, for each nu Henselian prime, we have such homomorphism. Now, so what this means is by the universal mapping property of restricted free products, we have this collection of arrows defined for each finite place. This defines a continuous homomorphism that we denote by non-abelian reciprocity in the sense of Langlands from this Weil-Arthur ideal group to LK. So this is one nice thing is that, okay, it depends on the existence of LK. When we abelianize, so abelianization of LK is the abelianization of WK. That's one of the properties that's expected. Then this map just lands into the global Artin reciprocity map. So, of course, these are defined up to local LK conjugation, by the way. Because of that, I introduced this local H conjugation thing in the first part. These are defined with respect to local LK conjugation. Oops, I'm sorry. And again, this arrow very much behaves this time like global abelian norm residue map. And moreover, Arthur gave candidate for this hypothetical group LK, and this hypothetical group LK, if I replace this with Arthur's, let's say, LK, then this result is compatible with Arthur's construction, but not only that, the conjecture that but this is of course meta conjecture to be precise, because I write a conjecture where one of the term is a conjectural object. This is open and surjective. So if this conjecture holds to be true, then we have a description of LK as quotient of this Weil-Arthur ideal group with a certain uh, subgroup that, yeah, wait, uh, with certain subgroup. And these are the references for part 2. Now, we are in reciprocity and functoriality principles. Well, having said that conjecture, the kernel, I call it isobaric subgroup of WAK phi, because when I quotient this out, if the conjecture holds to be true, I mean, one may have to modify the conjecture, by the way, but anyway, I mean, this is just these reflections that I have been doing for some time. Then, I mean, this quotient group, WAK, Weil-Arthur ideal group with this NK will yield the automorphic Langlands group. So more or less like automorphic representations or isobaric automorphic representations are determined by certain congruence relations then given by this kernel. So now we have a reductive group over K, and we consider G as a group over K nu also the completion. And we have the well-known L group of G in Weil form. It's the semi-direct product of the dual, Langlands dual of G with the Weil group. We have the L group of G nu of K nu also in Weil form. Then we have an embedding, natural embedding of these L groups. So the references here are more or less the references that I showed here. It's a subset of this actually. Yeah. So now I will introduce WA parameter of reductive group G over K. But before that, some terminology. Morphism over a group. So what does this mean? This means that I have two groups endowed with group homomorphisms. So my groups, let's say H and M. Wait, I have some time. And I have group homomorphisms H to W and M to W. We denote by PH and PM. A homomorphism F from H to M is called homomorphism over W if we have this triangle commutative. And semi-simple elements of the L group. So an element is semi-simple if the image under any n-dimensional representation is a semi-simple matrix in GLNC. And n-dimensional representation of the L group, we mean a continuous homomorphism. So this has two components, right? One is the Langlands dual, and the other is the Weil group. So when we restrict to the Langlands dual, it's homomorphism of Lie groups. I'm sorry. Wait a second. I'm sorry, yeah. And semi-simple homomorphism, if we have a group H, a group homomorphism F from H to the L group is called semi-simple. If every H is sent to a semi-simple element in the L group. Well, I mean, these definitions that I borrowed from Borel's well-known paper in the Corvallis proceedings, the one on automorphic L functions. So equivalent homomorphism we have H a group homomorphism between homomorphisms F1, F2 from H to the L group. They are called equivalent if we have an element in the dual so that F2 is given by the inner automorphism of G composed with F1. So there are some trivialities here. This is an equivalence relation, G-hat conjugation, equivalence class of homomorphism. We denote by bracket F. If they are semi-simple, then the equivalent one is semi-simple. If continuous, then equivalent one is continuous as well. So what's an L homomorphism? So let H be a topological group endowed with a continuous homomorphism. Oops, I'm sorry. H to the Weyl group. A semi-simple and continuous homomorphism F over WK is called an L homomorphism from H to the L group. So in particular, this is a quite general definition. The following definitions are in order. We have the global L parameter of G over K. So a group homomorphism LK to the L group. LK is the absolute the automorphic Langlands group to L group. We assume the existence, by the way. Let's suppose that this is an L homomorphism as in the definition above. Then its equivalence class of G hat conjugate of phi is global L parameter of G over K. And likewise, we have, okay, we denote global L parameters of G over K by phi kg. And we have the local L parameter. So again, it's semi-simple and continuous homomorphism from this time local Langlands group. Now this is unconditional. So if it is Henselian prime, finite prime, then this is isomorphic to the absolute Weyl group times SU to R. And if it is Archimedean, then it is just the Weyl group of R or Weyl group of C. This is an L over group homomorphism over the Weyl group of K nu. This is a homomorphism from L K nu to L group of G nu. We can assume this to L group of G. Yeah. This is called local L parameter of G nu over K nu, and the set of all local L parameters, they are denoted by phi K nu G nu this time. Now, this definition is kind of new. The other ones, they are borrowed from Borel, but this is new. So what's a WA parameter of a reductive group G over K? By the way, I mean, one has to put certain, later on one has to put certain conditions on the G, reductive group G, but I mean, I am not writing them. I mean, a semi-simple and continuous group homomorphism over WK, the Weyl group, we call an L homomorphism from the Weyl-Arthur ideal group to the L group of G. Now, its equivalence class is denoted by this. But this equivalence class this time is not just only G hat conjugates of phi. It is a bit more kind of general. I mean, it is locally G hat conjugates, as introduced in the first part. For the Langlands group, or we could have defined Weyl group or Galois group, the same things. For Weyl group, I'm sorry. Uh, there is no notion like locally G hat conjugate. It's just G hat conjugate. But here we have locally G hat conjugate. So we denote the set of all global WA parameters of G over K, but by phi K WAG this time. As I say, this equivalence relation is not G hat conjugate, it is locally G hat conjugate. So basic properties, I'm sure now you can guess, I want to invoke in the universal mapping property. So I take a WA parameter of G. An L homomorphism from WA to the L group. Then, so this is my phi, but I have this embedding of this local group, which depends only on K nu to Weil-Arthur ideal group. So via inverse of norm residue, so this is Artin, non-commutative Artin, let's say, non-abelian Artin. It is isomorphic to LK nu. So we have a group homomorphism from LK nu to LGC. So what does this mean? This means that there is a bijective correspondence between Weil-Arthur uh, parameters of G and product of uh, L parameters of G nu. So here the local G hat conjugacy comes into play in this correspondence. So it is defined like we choose one parameter, WA parameter, and it is mapped to all these phi nus that we have constructed here via this. So the theorem is we have a bijective correspondence between WA parameters of G over K and the Cartesian product of all local L parameters of G nu over K nu, as nu runs over all places, finite and infinite. So why this is interesting? So this has an application to global reciprocity principle for G over K. So let us recall global reciprocity principle. So we have pi k nu G nu, the set of all equivalence class of irreducible admissible representations of the local group, and the local Langlands reciprocity. So in order to discuss global reciprocity, I have to discuss local Langlands reciprocity in my discussion. Moreover, I have to assume local Langlands reciprocity principle. This is, of course, a conjecture largely. Of course, many cases are known, but like GLN cases, now a big theorem of Harris, Taylor, Heniar, Scholze, and for G2, Vitek, Gan, and Takeda, I believe. I mean, for small, uh, for other groups also. I mean, there are some known cases, but in the general setting, it's not known. But so what it says, we have a partitioning of irreducible admissible representations, the equivalence class of irreducible admissible representations of G nu in this form. These are all finite subsets. They are called L packets of G nu over K nu. I mean, description of size and so on, they are all known. I have not written them down. And they are parameterized by this elements in the L parameters. So what this means is that, and this is in such a way that we have a map from L parameters of G nu to the set of all local L packets of G nu. So it is given like this. And this bijective correspondence is not just an arbitrary set theoretic bijection. I mean, it satisfies certain naturality conditions, what they say. Like, I mean, for each side, one can write down local L functions, I mean, L factors, and they match. Likewise, epsilon factors, they match, conductors match. There seems to be some relation between their depths and so on. Um Okay, now I assume that local Langlands reciprocity holds for every well-behaved reductive group G. One can drop this condition nowadays. I believe one can drop this condition. But anyway, so let's be on the standard setting. So this assumption is not, how shall I say, some fantasy assumption kind of thing, because there is an ongoing work of Farg and Scholze, and they try to geometrize local Langlands. So their probably idea is, having geometrized the let me say arithmetical local Langlands, they will apply the uh, methods used in geometric Langlands side to this setting, probably. I mean, and many people are very optimistic that, uh, I mean, hopefully, I mean, local Langlands will be theorem, hopefully, for general G, I mean. Yeah, then having made this assumption, we have Flat's decomposition theorem. So if we have a irreducible admissible representation of the adelic group of G, then it has a restricted tensor product decomposition where each local representation, they are all irreducible admissible, and almost all of them are unramified. Therefore, uh, if I choose a WA parameter, phi, let me say, then it corresponds via theorem A that I described here. Where? Here. I choose a parameter here, WA parameter. Then it corresponds to a collection of local parameters. And they are all, these local parameters, they are all admissible. Okay. Now, but that is kind of, how shall I say, uh, we have one more restriction to add. Since this restricted free product that I introduced here, not here, I'm sorry, here, uh, almost all are unramified. So this Flat's theorem implies that we have global admissible L packet given by this restricted free product. And we can associate a WA parameter phi, denoted by like this, and lambda k global admissible L packets. But among them, we want the unramified, almost all of them unramified. So we have a bijection from WA parameters, but among the ones, so that each local, almost all the local components are unramified. So this is kind of a, how shall I say, uh, sub class of phi KWA, and global admissible L packets of this. So This one says that, moreover, so we have a concrete bijection here, up to here. We assume only local Langlands. There is no automorphic Langlands group or so on, but only local Langlands. We assume local Langlands, by the way. So, I mean, for example, GLN case is known. So then I can restrict my discussion to GLN case, then this will be unconditional. Moreover, automorphic tempered L packets, the corresponding one is an automorphic tempered L packet, is equivalent to the condition that this temperate kernel is inside kernel of phi. So for this phi. So there is also functoriality. A few words. How many minutes I have? Well, I'm about to finish. And so when we have an L homomorphism, then of course composing with the Weil-Arthur group, then we will going to have here a Weil-Arthur parameter. Via this row, we end up having a Weil-Arthur parameter on this side. Weil-Arthur parameter. So if I have rho from the L group of G to L group of H, then this rho describes a map from Weil-Arthur parameter of G to Weil-Arthur parameter of H. And they satisfy certain properties as well. So we have automorphic, but I forgot to write tempered ones here, kind of. This would yield global functoriality, but in crude form, of course. I mean, there is a much finer version also, but you see this WA is so kind of flexible by quotienting out certain things. I mean, one can shape it to fit into a more streamlined theory. So that's all I want to say, and thank you for your attention. So, yeah, that's all for
Mm.
what I will say.
Thank you very much. Are there any questions or comments?
So I will stop, or I will not stop share. I will keep it.
Yeah. Yeah. If not the case, let's thanks the speaker again. Thank you very much for interesting talk.
Thank you very much
Thank
for
you very much.
inviting me. Yeah.
Yeah.
So hope to see you later.
Again. Yeah. Thank you.
Thank you, Professor.
I am leaving.